You are so silent. Good afternoon, everyone. This is the best session in Prague. Sorry for the minute lost at the beginning. I'm alone, but Thomas is here remotely. The new Note well. Please, well, I guess you know, but please take a look at the latest version of that slide and the latest RFCs which it mentions. Very quickly, admin, I'll send the blue sheets. Today we'll have someone presenting from remote, in addition to Thomas being remote as well. So it's a first for BESS, so we'll experiment, but I guess it could go smoothly. Any comments on the agenda? Ali sent all his slides late, but since he was the only one at the bottom of the agenda, it didn't lead to any agenda change. Time management will try to be a bit strict, and if anyone can help me in taking minutes, I'm fine. I'd be glad, but I can live without it. Very rapidly, because we don't want to lose time. We don't have any new RFC for 9 months, which is quite a while, but not stressful. But we have 22 working group documents, which are quite lively. 3 are in IESG or in RFC editor queue. 7 in working group last call or waiting Shepherd write-up. Ali, we have one which is, I don't know the status. We lack some answers to the last call comments, and so I've pinged you on that one.
Yeah, the comments from Eric,
yeah,
which I'm gonna publish soon, and frankly, I'm waiting for the 2 drafts, E3 and EVPN overlay, and I'm, wondering what's the status for those 2. They're both of them. They're waiting for Alvaro. Is Alvaro here? Ah, here. All right.
Alvaro Rotana, to answer your question, yes, I'm here, and yes, the status is you're waiting on me.
So, with respect to one of them, just clarify the E3. You had a comment on the adding the IENA code request in the draft, and I did that. It was just a couple of lines of modification, and I would appreciate that. Is a very quick check if you can check and give a check mark on that. And then the EVPN overlay takes much longer to review. So that one, you can do it as your time allows. That requires brand new, your review from top down.
Alvaro Rotana, thank you so much for your consideration.
All right. And I'm gonna take care of that very soon. As I said, I've almost like a 70–80% through the comments, and the other 30% gonna be done soon.
Okay. Thank you very much, Ali. So it's a bit unusual, but we'll be talking about MIBs. Alvaro is wondering why. But we like work to be finished cleanly. So we had 2 MIBs, and nobody wanted to work on these. There have been a couple of people trying, but never managed to go up until the end. But we've Tsuno, who volunteered and who's going to do a quick update, is working very hard in addressing these charter items or milestones. Point it here because the receiver is here.
Hello, everyone. Can you hear me? My name is Hiroshi Tsunoda. I took over these two drafts from Jeffrey. So today I would like to just explain the current status of these drafts. So I have revised these drafts multiple times based on the MIB doctor's comments. And the first one is for the first one, I separated the textual conventions and the actual management object into different MIB modules. And in order to, based on the request from the MIB doctors, in order to improve the readability of the documents, I have revised the description class in the MIB definition and the background and terminology sections. Currently, I am revising I am preparing the latest draft according to the latest MIB doctor's review. So I think new revision will be submitted after this IETF meeting. For the second one, BGP MPLS Layer 3 VPN multicast MIB. So as you see the discussion in the mailing list, the MIB doctor suggested us to reconsider the design of MIB modules. So please understand that some more revision will be required to finalize this draft. So I really would like to give some comments from the especially technical point of view for the second draft. And I would like to confirm the purposes of these MIB modules. So for the first one, the purposes of the modules is to provide the textual conventions to represent the tunnel type and tunnel identifier. The other purpose is to provide the p-tunnel information to other MIB modules designed for monitoring and or configuring L2, L3 VPN multicast. The purpose of the second MIB is to monitor the operational information of the L3 VPN multicast on provider edge routers and to configure MBRFs and PMSIs on the provider edge routers. And of course, to provide the notification mechanism to the network administrator. So this is my understanding. So please let me know if my understanding is not correct.
No, it
Oh,
no, sorry.
sorry.
Okay. No.
Oh.
Try again.
Okay. And according to the MIB doctor's comments, he said there may be the problem in the coverage of MIB modules. So actually, the second one, the BGP MPLS L3 VPN multicast MIB, currently does not have information object to represent these information components. So I think these are required for managing and configuring the L3 VPN multicast. So I am thinking to add the management object for representing these variables into the MIB definition. So what's next is I'm really seeking the input from the working groups. So especially from the technical point of view, I am not an expert in this area. So please give me some comments. So for example, if there are any information that should be included in or removed from these MIB modules, so please let me know. And especially the comments on the use case scenarios of MIB modules are really helpful for me. So anyway, I would like to keep working to finalize this draft. So the comments are always welcome. That's it. Thank you very much.
Jeff, as a very brief comment, you probably should not put anything into the MIB to limit the generation of BGP update messages. That's a piece of the generic BGP infrastructure, and this is not something that could be really controlled under this module.
Sorry, one more time, please.
Previous slide.
Okay, this one.
Configuration variables. Rate limit BGP messages. Don't do that.
This one.
Yes.
Okay, thank you very much. Anything else? Okay, thank you very much.
Thanks. Adrian? York.
Thank you. Thank you for the 4 minutes, 59 seconds you've awarded me. I'm Adrian Farrell. I just want to do an update, quick update on draft BESS data center gateway, mainly because although the file name says data center gateway, this is really now segment routing enabled domain gateway as follows. So when we started this, we were interested in data center sites that were running segment routing and wanting to connect across non-segment routing backbones or segment routing backbones. We've revised that just to generalize the concept for any domain that is segment routing capable. Largely speaking, that required a global search and replace in the document and not very much else apart from going back and looking at all the changes and saying, no, I didn't mean that one. The work is stable. It's referenced by a document John and I wrote to provide a bigger landscape. So this document is doing the protocol bits and pieces, and the new document provides a landscape, and that's targeted at the Spring Working Group. So a reference model, a picture, 2 domains that are doing segment routing, and some backbone made up of 1 or more ASs with multiple homing. And we want to be able to steer traffic right the way across from a source in one domain to a destination in the other domain. So we want to do segment routing end to end, and actually traffic engineer how that traffic goes across those ASs, which points of interconnection it uses. So there are 2 aspects we have to handle. One is gateway discovery. How do you know what other gateways are out there? Firstly, what are the gateways to your own domain, and what are the total set of gateways that are out there and providing reachability into domains? Very briefly, we use a route target to auto-discover, and we then install import rules so that only the gateways to a domain import the routes to that they care about. So all gateways to the same domain will import each other's routes and then auto-discover the current set of gateways to that domain. The other thing we need to do is understand how to get connectivity across the backbone. So what we do is when a gateway advertises reachability, it includes a tunnel encapsulation attribute with a new TLV, basically saying here is reachability to an SR domain, and we can put in a SID there as well if we want, which allows the other end of the tunnel to build a full explicit, if you like, explicit path, segment routed explicit path. It's been suggested to us that reading the other document, that the full framework actually gives a better background to why these protocol bits and pieces exist. But I think it's still worth keeping the 2 documents separate. So the whole magic is when a gateway to a domain discovers other gateways to the domain, it actually also adds those to its advertisement. So back in the original picture, there are multiple ASBRs along the path, and they might start dropping paths because they're not optimal. Well, you want that information to make it all the way through. So by having all the gateways advertise all of the other gateways, you actually get that through. Combining that then with BGPLS and EPE, you get the ability to do full end-to-end traffic engineering. So we still need to write management and security sections. We need to make a first-come, first-served code point request, which will obviously involve us also talking to IDR. It would be silly for us to make protocol extensions here without talking to IDR. And we would like more reviews, especially, as I said, in the context of the document that gives much more background. It's a really simple draft. Turned out that we didn't need much in the way of protocol extensions. And question for the chair, it's traditional. Can we adopt it? Is it appropriate to adopt it in BESS, or should it go to IDR? And what more would we need to do to start the adoption?
You don't need to do much more. I'd just like to have a sense of the room of who has read it. Okay, thank you. So I guess we'll pull the list.
I have Wim Hendricks knocking. I have one comment. There is an alternative solution to this, which is being standardized, which is the BGP SRTE policy framework, which is being discussed in, I think, segment in Spring and in IDR, as far as I'm aware. And that does actually, if the use case is traffic engineering between data centers end-to-end with segment routing, that is actually what it's also supposed to do. And it's using binding sits and stuff like that.
So I'm not a fan of having beauty contests.
Oh, I'm just wanting to point out that there's
another document out that does something else. Yes, we are aware of it, and the reason we wrote this was because we think that other approach is not so much broken as because if it was broken, it could be fixed. It's just not the way we would do it.
I think what my personal view is that the SRTE policy framework is even, you have more options, or even it's more extensive because you can have even multiple paths across multiple pieces of the network, and you can actually do even more complicated traffic engineering than what you're suggesting here, in my view. But we probably need to go to the details.
Yeah, I think we might. It might be worth looking at that in the context of the new Spring document that's on this slide, and just saying, okay, so that's actually what John and Adrian are trying to do. Sure. Would the BGP SRTE solution achieve that as well?
Right. Yeah. Yeah. I think we need to I think understand and look at it. I haven't done all the due diligence myself, but I do know that that document is actually addressing the same use case more or less.
Jeff, so to address that last comment, the TE policy document is really more about traffic steering of different types. So it's really about tunnel selection, to be able to put traffic a specific type on there and to bind those tunnels to the individual BGP routes. So it's potentially usable in some of the same context as this, but only in the sense that both of these are sort of BGP and SR, and view of the network can let you do this. This is more about actually how to tie the different domains together.
Yeah, but so if you use in SRTE policy a binding sit which represents the data center on the other side, you actually achieve the same thing.
That's true, but your visibility points change a little bit, and that's a lot of what this document is giving you is visibility more than in terms of choosing how to bind the traffic. So the TE policy is about colors on the routes. That's really what it's about.
Yeah, but also the TE part.
That's true.
Yeah. So I think my comment is, Wim again. So my comment is basically, we need to look at those two alternatives and figure out a way forward, probably, rather than trying to come up with two things which are competing a bit. And we need to look in. My suggestion is that we need to understand what are
Yeah. So I hear your suggestion to read the document.
Yeah,
I did read this document, and I read SRTE policy. So in my view, SRTE policy is more expensive. It's actually more extendable and actually does this use case.
it is definitely more kitchen sink. So I don't think they're actually incompatible, but I think they do have some overlap.
Alice and Jesse, so I'm wondering, given that this draft is, as you mentioned, talks about the specific implementation and aspects of the framework draft, should we do the working group? Should we wait for the working group call on the framework draft before adopting this one?
When you say framework draft, do you mean the one that's cited there?
Yes.
Frankly, we could if the spring working group would deign to meet so we could discuss it.
Okay.
But I'm kind of reluctant to delay the necessary protocol work that people want to implement, waiting for a working group to discuss an architectural framework. Difficult.
Because
you could always discuss it on the list.
Yeah.
It takes it. Yeah, I mean, discussing is you have to talk to someone when you're discussing, otherwise you get bored.
So another question is: this draft the only draft related to this arching draft, or there are other drafts related to this?
This named document here points out at lots of other pieces that all come together.
And those other pieces are you doing it in other working groups?
Those are other pieces that already exist. So basically, when we did the work that's in this document, we found a gap.
Oh, so this is the only gap.
And the one I've just presented fills that gap.
Okay, all right.
Thank you.
Excuse me. Hi, I'm Lou Berger. I'm going to be giving an update or an impact discussion on how the network instance model work that's taking place in the routing working group is going to impact layer 2 and layer 3 VPN device models. For context, we have broken down the representation of virtualization that happens on network devices into two things. We have something called logical network elements, which are separately managed partitions of a device. And then we have network instances that we use to model VRFs and VSIs, layer 2 and layer 3 VPNs. That's what we're going to focus on right now. I'm going to try to skip a bunch of slides, but I want to say one thing that's important here. We model both using a new capability within Yang called schema mount. What schema mount allows you to do, someone else used this analogy, I really like it. You use a whole module, you treat a whole module as a grouping, meaning you can import a whole module in a different place in the tree. And that's what we're using here as a fundamental building block. There's a tree representation, you can go read about it. Here's our basic model. We have something called the network instance. It's a top-level module. You'd see it at the root of a device. And we instantiate what we call a network instance per VRF or per VSI. We have an NI type, network instance type, that we would expect to be specific to every layer 2 or layer 3 VPN technology. So if you have something that's specific to BGP layer 3 VPNs, it would go here. If you were going to do EVPN, it would go here as a different type. This is really the PE information, PE-facing information used to support a VRF or VSI. In order to support the modeling of information that's in the network instance context, in the VRF context, in the CE context, we produce something called these root types. You can have one of these, and it's an implementation's choice which they use. You can read the draft as why we have 3. That's really a Yangism, but logically you can think of there's a place where you drop your VRF or VSI representation. This is, again, what would be used to model the information that goes to the CE side. And that is, you would put there any top-level module. So, whoops. Somehow, there we go. So what do I mean by a top-level module? Underneath a L3 VPN instance, we would have some L3 information that would go in the PE-facing side, and you would have put routing information underneath the VRF route, and you could have OSPF, if you're running OSPF between the PE and CE. You could even have RIP if you really want it, or BGP, or whatever protocol makes sense. The schema mount has a notion of instantiating new data through this schema mount mechanism. So every instance gets its own piece of data. Even though the schema is the same, the data is instantiated per, in this case, network instance. The data that's reinstantiated has a slash after it that's mounted modules. You can also, from this is a Yangism again, the ability to, you can reference information from within this context to information that's outside the context. For example, you could have something inside OSPF referencing the interface information at the top level through something called a parent reference. I think of it as a symbolic link. That's why it looks like an @ So this says you can reference information. These models, the mounted modules, can reference information at a top level. When you're from a client side, you wouldn't actually be able to retrieve anything underneath here. You would go back to the top level. So in terms of impact, we think there's 3 areas of impact. You have core facing PE information that is not instance specific. So that's not per VRF. That goes either into the protocol like BGP, or if you don't have a home to put it elsewhere, you can put it at the top level network instance. We really think that's mainly going to show up in the protocols. If you have core facing information that is per instance, that goes under NI type. And then all CE information goes under VRF. Again, what shows up here is an implementation time choice. So we don't specify it. We don't tell you that you should be doing it. We're not saying this working group should tell its vendors what to put inside the CE-facing context. That's the vendor's call. But what information gets configured in order to support a VRF in, let's say, example, BGP, your RTs, your RDs, that goes under NI type. That's it.
Thank you.
This is going to be followed up by 2 presentations, one from the L3 VPN authors, the other for the L2 VPN authors, sort of thinking about how they fit in. Maybe it makes sense to wait to hold questions until those are presented.
That's it? It's the next set of slides, or it's the next? This one? Okay. Give me 1 second. That one. What is that? Oh. All right. That one.
Yep. Hi, I'm Dhanendra Jain, Cisco. I'll be giving an update on L3 VPN YANG model, and as Lou described, the changes that will be coming because of the network instance related changes. So after the last IETF, there was a revision submitted in L3 VPN YANG model. That mainly is about removing the private definitions of some of the data types like RD and RT and reusing them from IETF routing types. Besides that, there are a bunch of updates in progress. Mainly, they are following. One is NMD alignment, which is removal of state containers, which are really reflecting the applied config state, and those have to go away from the model. Secondly, alignment with the network instance model. As Lou described, earlier the model was augmenting network instance container conditional upon the type of network instance as default versus the named network instance. This has changed, and what's going to happen is, and as more details coming in the next slide, based on NI type as L3 VPN, some of the portions of the model content will go in there, and BGP related augmentations for L3 VPN, which fall under the category of core facing configuration, and then per instance configuration in BGP, those will have to be placed in the right places. So here is an example of it's a Yang tree depiction. RDs and RT kind of configuration. It is per network instance configuration, which will be available under network instance under a particular network instance, with case being NI type as L3 VPN. The second category is BGP specific L3 VPN extensions. Those are still per network instance extensions, and those can go in here as well under L3 VPN case, NI type being L3 VPN. One example of that is label allocation mode, which is per network instance configuration. Then the second category is for BGP specific extensions. The second category is core facing instance configuration like ASBR options. And one example for that is ASBR option be pairing the retain route target knob. And such knobs will go in the augmentation of BGP model at the top. And it was mentioned earlier that the whole routing model and control protocols and a protocol BGP under that is mounted under a network instance by using schema mount. But here, because we are augmenting the top BGP container and L3 VPN is a separate module, we can control it we can control it in such a way that it won't show up in the context of per network instance under the schema mount. So this way we can achieve the three categories that were described in Lou's presentation. The L3 VPN top configuration, and then the BGP specific configuration, which is per network instance, as well as for the core facing instance. So as next steps, we'll be submitting revision 02 with all these changes. Then we'll be requesting a detailed review of the model. And then once all the review comments are addressed, we'll be in a situation to think about work group last call. I think next is L2 VPN update.
Patrice Brissette, Cisco System. Okay, so today, just as a follow-up of the boring stuff at the beginning. So let's go with L2 VPN. So I'm going to be quick. Basically, what we've done is we just tried to finalize the Yang model, so we can also call the workgroup last call very soon. So we've been doing the all the details about the pseudo wires. Also, make sure that we are compliant to NMDA style, and we play also a bit with the instances. Make sure that peoples are happy. We name it a bit. So have a look at the latest. I think we are very close to get it done. So and hopefully. And on the EVPN side, well, there's the same thing for the Ethernet segment Yang and the VPN Yang. We tried to finalize pretty much everything. We had the last bits and bytes, and like bits and bytes is at 7. Anyway, and the pseudo wire stuff also that we added recently to the Ethernet segment. So again, try to align the model with the NMDA. So on the VPN side, again, all the last stuff that we've been doing. So we added the VPWS VNN aware to it, pseudo wires, reshuffle a bit the model between the interaction between L2VPN and EVPN. And also mainly for all of them, L2VPN and those two models, is we added the state change notification, so everything which is opera data. So that one, unfortunately, the team wants to apologize. We got issues to upload the latest draft. You're gonna see it very, very, very soon. And then what we're gonna do is send an email on the list, make sure that people pay deep attention to it, and the work will be done on that. Thank you.
Thank you, Bethis.
Yes, Manchu.
Himanshu from Siena. I wanted to give one update. There was a presentation in the PAL working group about the pseudo-wire Yang model, and we basically said that we are doing that in the BESS, so we have to consolidate into a single pseudo-wire Yang, the container that we have here. I think the only other things there is the pseudo-wire types, ATM, frame relay, all that, and multi-segment pseudo-wire. So rest of it, we have it covered, but some of that other things, we'll pick it up. Okay,
thanks for the update. Any other question? All right, thank you.
Thank you. Merci, Patrice.
Hi, I am Satya. So the talk will be on the BGP multipath in interrace option B, and it's a simple idea, and the problem exists today, so just thought of writing a draft on this. So what is BGP multipath? It's like when you have more than one path to the destination in the forwarding, right? And it's used for load balancing and redundancy. And it's a standard concept. Almost all the vendors support it, but there is no standardization in the sense that there is no internet draft or RFC which says like what are the requirements for the multipath, but pretty much everybody kind of assumes that they agree on some set of ideas, although it's not in paper. And most implementations take into account that the next hop of the path, that needs to be unique, right? In the L3 VPN case or any VPN case, there is also a label along with the next hop, but that has not been taken into account. So I have a very simple diagram just to put this problem in perspective. And I have a case, an iBGP network in which R1 is the source router and generates a prefix 1.1.1. And that is propagated via two route reflectors, and then it goes to the destination, which is the R2, the receiving router. And the route reflectors do not set the next hop to themselves. So in this case, even if there is multipath configured at R2, it's only going to install one of the path in the rib and then in the fib. It is going to reject the other path from RR2. It won't take it as a candidate multipath. Okay? This is a very standard, straightforward thing. Now, if we decide to change the next hop at the route reflector using like next hop self, which is again very standard, then at R2, we will receive both the paths, and they will have different next hops, and then both will be treated as candidate multipaths, and they will be eligible, and then both the paths will be in the fib. Just a quick introduction to interrace option B. This is defined in RFC 2547. And here the control and the forwarding over the ASBR or the autonomous system boundary routers, both the control plane and the data plane is across these ASBRs. And the next hop is reset at the advertising ASBR. I didn't write it, but there is an option whether you want to reset the next hop at the receiving ASBR also or not. So again, just very standard diagram. We have a VRF or the VPN existing at P1 and P2, and the advertisement is across an AS from AS100 to AS200. So the C1 is sending a prefix 1.1.1/32, and at P1 it is in the context of the VRF. It's advertising with attaches a route distribution RD1, and then at ASBR1 it has to set the next hop to itself, right? And notice that in P1 the advertisement came with the label L1, and in ASBR1 it is set to L2, right? And then it goes towards the receiving AS, which is receiving AS200, and there I just choose that on ASBR2 it is not resetting the next hop, which is kind of standard behavior. Now we take a case in which the C1 is dual home to P1 and P2, and as in the previous figure, here the VPN prefix on ASBR1 changes from label L1 to L3 and then goes towards C2. And split second later, the same advertisement, or rather the advertisement for the same C route 1.1.1 is sent to P2, and P2 attaches its own RD, right, which is RD2, and it goes to ASBR1, which again rewrites the next hop and the label. So what happens is on the P3, once both these advertisements are received, it is going to install only the first one, right? Because the next hop is same, right? So that's the key thing. So there are a couple of ways we can do this, like how do we make both the paths to be multipath eligible at P3? One is we can use a different next hop policy at the SBR. So the policy could be that if next hop is incoming on the inbound policy, if the next hop is P1, we can set it to some loopback. And that loopback is generated at ASBR1 and then sent towards the receiving AS, because you need reachability for that loopback, right? So, but that would entail some configuration over it, and we don't want to clearly do it for every kind of next hop. So the second thing we could do, and I think that is easy fix, is we can use the tuple next hop and label when determining the multipath at the receiving P. So in the from the previous figure, even if the next hop at the receiving P, which is P3, is same, ASBR1, then that's the next hop, the labels are different. So then both the paths can be programmed in the forwarding, right? So what happens is, if, for example, I am now wanting to send traffic from P3 towards C1 for two different source nets, which I didn't show, from two different sources, and the destination is the same, which is the 1.1.1 at C1. From P3 to SBR1, there is only one LSP, right? I mean, even though there's like separate labels, rather I should say the path is the same. And then at SBR1, what happens is the traffic can be split up according to the labels that they get. So in this way, we can utilize the available paths in the AS100, which otherwise we are not able to use today. So that's pretty much the talk. Questions?
Thank you, Tati. Five minutes. Sami.
Hi, my name is Sami from VMware. So I'm going to be presenting a draft on Genève with EVPN. So Genève, as you folks know, is an NVO3 encapsulation. It's being adopted now as the standard for the NVO3 encap. And EVPN currently as a control plane does not use Genève as one of the tunnel encapsulation option. So this draft is about extending the tunnel encapsulation options that EVPN support to include Genève too. One unique thing about Genève as well is that Genève allow the tunnel to carry option TLVs. So it's an extensible tunnel encap that allow option to be transmitted along with the tunnel encap. So EVPN control plane can play a role here as well on negotiating between the network virtualization endpoint what kind of option can be transmitted or received along with the tunnel encap. So we are defining a BGP extension here that will carry what options that will be present in the tunnel encap after the tunnel header. And as shown here, those are going to be carried, those tunnel option types are going to be carried in a new tunnel encapsulation attribute sub-TLV. So we are going to have a sub-TLV type for each option that will be carried. And it's a regular TLV format similar to what Genève is going to be carrying in the tunnel encap. So in terms of operation, the BGP encapsulation extended community is currently being carried on all EVPN routes. That BGP extended community is carrying the tunnel encapsulation attribute, tunnel type, to be the Genève tunnel encapsulation. And the tunnel encapsulation tunnel sub-TLV for the Genève will carry those tunnel option sub-TLVs that can be transmitted and received. The operation is straightforward. So if an NVE is expressing what option has to be carried on the tunnel encap, then he is not expecting that the other NVEs to be sending any tunnel encap, any option other than what he is capable of receiving. I think, yeah, that's about it in terms of operation. So for the next step, of course, we have to update more because actually Genève tunnel encap carry as well next protocol. It has some other as well parameters that can be negotiated or signaled between the NVE endpoint. So I think we are going to be progressing the draft as we are solidifying more the control plane requirement from the NVO3 stand. So so the draft definitely is going to be progressing, or we are going to be adding more meat and more information to it as we go, and as we are as well solidifying the requirement from the NVO3 stand. So I think that's about it. We can have comments now.
Greg Merskizity. So this is a control plane for NVO3 or specifically for Genève?
It's a control plane for Genève, for the Genève tunnel encap, but as well, given that Genève is the standard for NVO3 encap now, or is going to be the adopted standards, and you can say as well it's a control plane for the standard tunnel encap, right?
Because it might be, well, given some developments.
It's a solution draft, so this is why I was talking more about we need to solidify more a requirement for the control plane, and this is work that's going to be done by NVO3. So NVO3 working group is working as well on solidifying a requirement document. So this solution document can progress as we are solidifying more the requirement too. This is what I was trying to say.
Okay. Any plans to address other NVO3 encapsulations?
No, only Genève. So this solution document is focused on Genève only.
Previous one? Yeah, we just added. Just a clarification with your answer to Greg. with respect to the VXLAN encapsulation, there is already, a draft that is going to become, EVPN is a control plane for VXLAN encap and is going to become RFC soon. It is sitting in the pipeline. So when you're talking about other NVO3 encapsulation, if it is VXLAN, yes, it is already there. If you're talking about the, GPE or GUI, then as needed, we can add it. I mean, this is, EVPN is a general control plane that can handle any kind of encapsulation.
Correct. The scope of the document is still Geneva, right?
Right.
So,
Jorge Rabadan, Nokia. Just an open question. So if we are defining options specific to EVPN, I understand this is the right document, right? But
correct.
if we define something specific to the Geneve header, I guess it has to go to the Geneve draft. Like if you want to take one of the reserved bits in the header, right?
Yeah, definitely. Okay. If I think for your comments, Jorge, on the multicast bits, or as well as other comment about the local bias and so on, if we are going to be defining an option TLV, that goes to NVO3. If we are going to be changing something on the header, goes to NVO3. But if you are going to be signaling between the NVE, what's going to be available in the header or available as an option, then we need a control plane for that, or signaling to be done, right?
Yeah, makes sense. Thank you.
Thank you, Sam.
Good afternoon. My name is Jorge Rodan, Nokia. This draft is about loop protection in EVPN networks. Here you have my co-authors. And what is this about? Is about you have an EVPN broadcast domain and you need to get it protected against loops. First consideration, there is a distinction between a local loop and a global loop. What is a local loop? Is something local to a node. For instance, in the example here in the diagram, you have on PE2, for instance, if you receive traffic, let's say broadcast from host 1, and the traffic goes out AC2, attachment circuit 2, goes to SCE and comes back somehow, that is a local loop. It's a loop that is within the same port, same broadcast domain. In PE3, you have the same thing. So it's a local loop because it's actually within the same PE, right? And same broadcast domain. So those two cases are not addressed in this draft because the assumption is that the local implementation should be able to deal with them. What we are addressing in this draft is a global loop that is caused by a backdoor link somewhere in the between CEs that is causing, this in this example, this loop between P2 and P3. So this is what we are talking about, these global loops. So what are we doing to prevent that? So what we are doing is basically completing the RFC 7432 MAC duplication mechanism with an optional loop protection procedure. It's fully compatible with the base EVPN specification. It's not adding any control plane piece of information. And the only thing we are suggesting is upon detecting a loop based on MAC duplication event, you should carry out some of the following loop protection actions. So the P should discard, the P detecting a loop for a given flow should discard that flow that is in loop, and while allowing other flows. And optionally, the P can also bring down the AC where the loop was detected. So what you have in the draft is it's not working. Sorry. Yeah, so in the draft you have this diagram, a bit uglier, but basically it's an example with two P's, P2 and P3, and you have a local attachment circuit with MAC2 injecting broadcast traffic, And P2 and P3, they are part of the same EVPN broadcast domain. And you have also a backdoor link between AC3 and AC4. Obviously, you have a loop here. So the way we detect it is actually taking advantage of the MAC duplication procedures in the EVPN. And those procedures, basically what they say is, if I receive, if I learn a MAC locally in AC2, I re-advertise it. At the same time, I'm sending that traffic over the backdoor link and over the core. Obviously on P3, I'm going to receive the route, but I'm also at the same time, I'm going to learn the same MAC locally on AC4. So I'm going to re-advertise the MAC with a higher sequence number and so on and so forth. At the end of the process, when you reach a number of moves, of MAC moves, you're going to declare that MAC address as duplicate, right? And all this is specified in EVPN. So the new thing we are doing is, once you detect that MAC2 is duplicate, and you add it to a duplicate MAC list, we are taking some actions. So what RFC 7432 says is, basically the action is, if P3 is detecting MAC2 as duplicate, it has to stop advertising MAC2 and log an event, and that's it. So we are extending that, and we are saying, well, P3 should actually start a retry timer, and P3 should actually trigger some loop protection actions. And those actions are what we should black hole MAC2 in this example. And a black hole in this context, what it means is that MAC2 should be installed in the bridge table as a black hole MAC address. Black hole MAC address is not associated to any attachment circuit or any EVPN tunnel. It's just a black hole MAC. And what that means is, from that point on, for any ingress frame on P3, if the source MAC address is MAC2, the frame should be discarded. If the destination MAC address is MAC2, the frame should be discarded too. And as an option, we are also suggesting that if you want to be more restrictive, you can actually, as soon as you detect an ingress frame with a source address MAC2, you can actually bring down the attachment circuit. Now, the black hole MAC is something that you can flush after the retry timer expires, or with manual operations, or even if you receive a better MAC route for the MAC. So what is this draft informational? Well, because it's compatible, fully compatible with the 7432 procedures, is not modifying any EVPN routes, and can be deployed even if you don't support this in all the Ps in the broadcast domain. Obviously, it will help better if you support this in all the Ps in the broadcast domain, but it's not necessary. And why do we think it's important? It's because the backdoor links happen, and actually, as a co-author in the draft, we have an operator, and they are concerned about these kind of loops big time. And obviously, we want from the working group to provide some feedback about this work, and comments are appreciated. Even Ali's comments.
Especially my comment. So basically, the detection mechanism is already, you're leveraging the detection mechanism, which is already in the RFC 7432.
That's right.
Right, and RFC 72 discusses how to take care of the control plane and, stop advertising the MAC addresses and notify the operator.
Mm-hmm.
And here, basically, this discusses what action to be taken on the data plane by stopping the traffic flow and optionally disabling the attachment circuits.
Yes.
I think so that is fine. It just for that aspects of it, frankly, the draft is too verbose. You can condense that to a couple of pages. I would say max. I hope you don't take this comment the wrong way. It is awfully lot of requirement definition and discussing too many things to capture the essence of what the draft is doing.
The reason why we decided to put this together is because the MAC duplication section in the RFC we thought it was not clear enough. And
no,
that's why
I don't
we
have
added.
the problem with having a draft to talk about the data plane action, and the result of the data plane action is to make sure, to prevent the loop in case there's a backdoor. That's fine. I'm saying, for that, fine, let's have a draft. But having a 10-page draft for something that we can write 2 pages for, I think I'm saying the draft is a bit verbose, if you can condense that.
All right. So if you have any comments about what parts of the draft are not needed or whatever?
Sure, I'll send it to you.
Okay, thanks. Any other comments?
Satya from Cisco. So can you go back to the slide where you have the... Yeah. So on AC3 and AC4, are they on the same ES or different ES?
On the same what?
Same Ethernet segment or different?
No, different.
Okay. Because
yes. If they are in the same Ethernet segment, there is no loop.
Okay.
Right? Okay.
Training.
All right, so one more draft. This is PIM proxy in EVPN networks. This is the list of my authors. And basically, this draft is a natural evolution to all the work we've been doing in EVPN. The idea is, if you have an EVPN broadcast domain, we've been optimizing EVPN to take care of the flooding of the ARP messages, enable discovery messages, even IGMP, MLD, and all that. So we didn't have the same thing for PIM. And the idea is, if you have some PIM routers that are sharing like a LAN or an EVPN broadcast domain, you should actually do something to optimize the flooding that you get. And here you have an example in this slide where you have a broadcast domain, an EVPN broadcast domain, and you have some multicast routers, some non-multicast routers, and some hosts. And if one of the multicast routers sends a hello, a PIM hello, that gets flooded everywhere, even to the attachment circuits where we don't have any multicast router. Same thing with PIM joins or PRUM messages. They are flooded everywhere, right? So we can do better. And along the lines we are doing with IGMP, we can do actually the same thing with PIM. So the objectives of this draft is to reduce and eliminate the PIM message flooding in the core. We also want to forward the IP multicast streams efficiently. We are also improving the assert mechanisms that we have in PIM with the help of this PIM proxy. And along with this, we are also providing support for all-active and single-active multi-homing with synchronization of PIM states. So these are the procedures that we have in the draft at the moment. I'm going to go through some of them. So the first one is the what we call the multicast router discovery. So we are defining a new EVPN route type that we call MRD, multicast router discovery route. And this route is actually replacing the PIM hellos in the core with the BGP route. It's actually replacing the soft state hello messages with the hard state BGP route. So the idea is at the access, you receive hello messages, PIM hello messages from routers, and you add the PIM router to your neighbor database, and you trigger this multicast or MRD route. And you take there the IP address of the router, the secondary addresses if you have such a thing, DR priority, and that's pretty much it for the time being. You handle the timers and the gen ID and other things locally. The receiver piece, basically based on the routes, we add the multicast routers to the neighbor database, and you generate the hello messages again. We take advantage of the same route to also auto-discover IGMP queries. So there is a flag in the route where you can actually indicate whether the route is a querier, right? And in that case, we with just one route, we discover both things, so PIM routers and IGMP queriers. You have a question about this?
Yeah, so Stig Venas. So in PIM, you know, we have a lot of other PIM options or hello options. And there are some that potentially could be useful, like DR load balancing, or there could be, well, other things.
Yep.
So I'm wondering a little bit if it would make sense to, instead of having a fixed format like this, so maybe allow like a list of hello options to be in the route, and it could be kind of implementation dependent, perhaps which hello options you choose to actually include in the BGP route.
Yeah. So we thought about the rest of the options because, yeah, in the I agree with you in the hello messages there are lots of them. Basically, we decided to put in the NLRI just the main ones that we thought were important. We also decided that it was some of them, like the timers and GenID, it doesn't make sense to propagate that in a route.
Yeah, I agree. Yeah.
And for some other options, we thought, okay, maybe in future revisions we can add some TLVs or some attributes or something like that. But if you have some feedback about what options we must include, for sure, we would appreciate
Yeah,
your
so
feedback.
I would say, so two things. One is, I wonder if the format should maybe be more flexible, so you know it's easier to add new things later. And the other thing is, yeah, if you make it more flexible, you can still recommend which ones should be used. Or if you choose not to make it more flexible, yeah, then we should discuss exactly which ones should be there. But yeah, just thinking it's worth thinking more about this.
Okay, we appreciate the feedback. All right. So next one is, obviously we also need to do something with the PIM join and prune messages. So basically here what we want is if we receive a PIM join for the same source group or star comma G, basically we can do proxy and generate a single route summarizing that. We are reusing here the SMET route, which is the same route that we are using in the IGMP proxy draft. And the only difference is that we are extending a little bit the route. So in the flags field, there will be a new flag. We call it P flag. And that is indicating that we actually received a PIM join from a PIM router. And the information there is also applicable to PIM. And when that happens, basically, we need also to add the upstream router information, which is not needed in IGMP. Along with that, we are also introducing a new route type, the RPT prune route. And the reason why is because we need a state for the S, G RPT states, right? And we need to propagate that in BGP as well. An important thing that we are doing is we are optimizing the PIM assert procedures. So one of the things is when you have a bunch of PIM routers with sharing a LAN, sometimes you may have two or more upstream multicast routers injecting the same multicast content, and then that actually trigger assert mechanisms, and we could do that and just let the assert messages do their thing. But we thought that, since the assert mechanism is actually painful for the routers, and we don't want any duplication in this EVPN broadcast domain, we thought that we could do better. So actually what we are doing is, if we receive PIM joins for the different upstream routers, we are actually making sure that we don't have any duplication in this EVPN broadcast domain. So we divide the procedures in procedures for the downstream piece and upstream piece. So what we do in the downstream piece is, and here you have an example on P1, if we receive a PIM join for, let's say, a star comma G, but with different upstream neighbor, P1 is going to pick up the higher IP address as the neighbor, and is going to send a single SMET route with IP5 in this example. Now, for the upstream PEs, if they receive 2 or more routes for the same S, G, or same star, G, or star, G and S, G, but different neighbor, different upstream neighbor. So basically the procedure is the following. So in this case, P3 and P4, they will pick up only one upstream neighbor. It'll be, so the neighbor coming in the SMET for S, G is preferred over the star, G. So in this case, they will pick up R4. Now, once they do that, basically the Ps, they instruct the data path to discard multicast traffic coming multicast traffic for S1, G1 coming from a different router than the selected one. In this case, P4 would discard multicast traffic for S1, G1 coming from R5. And immediately after, P4 will actually send a PROM S1, G1 IP5 RPT message to R5 so that R5 stops sending the multicast traffic. So with this, basically, there is no way you can have duplication in this shared EVPN broadcast domain, and we avoid the assert mechanism between R4 and R5. Yeah, finally, talking about multi-homing a little bit, just as we do have in the IGMP proxy draft, when you have multi-homing, it may happen that R1 sends a join message to P1, and we actually need to synchronize that state in P2 as well, if P2 is part of the same Ethernet segment, right? The reason why is if you have a failure on P1 or the link, P2 must have already the state in order to be able to do a fast failover. That's the first thing of the synchronization. The other thing is, because now we are building the hello or the PIM neighbor database based on not only on hellos, but also based on the MRD route. The MRD route also has to be tagged with the Ethernet segment identifier to actually synchronize the PIM neighbor databases. And that's pretty much it. So with this, basically, we complete the set of multicast optimizations for EVPN broadcast domains. I have here that we need to agree on the route types to be supported. We already met the IGMP proxy and the authors of this draft, and we agreed that we would reduce the route types as much as we can. And an open question is whether we need to support any other procedures like PIM bootstrap or RP discovery or even dense mode. And yeah, we need some more feedback and comments from the working group.
Just trying to be quick from time perspective.
Very good question. Slide 6. When we are trying to prevent another for the S1, G1, dropping it on the PE4. I mean, from dropping on the PE4, so PE4, I'm guessing not to forward it to the PE2, right?
To forward to the broadcast domain in general.
So for the core, a split horizon would take care of it, wouldn't it?
No, it's basically if R5 injects traffic for S1, G1, right, into P4, this is broadcast domain, so it would actually flat to the rest of the Ps, right?
Right.
So we want to avoid that. Right.
And then there is the other streams it comes from R4 to PE3, and PE3 sends it to the broadcast domain, right?
Yeah. So we want the multicast content coming from R4 because this was the selected upstream neighbor.
All right. That's all.
Stigman has. So back to your conclusions. I know there was some work in the past on trying to do BSR over BGP, but it gets pretty complicated. I'm not sure if it's worth the effort, but at least there is some work if you're interested that maybe you can look at Not sure if you want to support dense mode, but it depends what people deploy. But generally, trying to get people away from dense mode, and
That's what I thought.
PIM binder might be more relevant, perhaps.
Yeah. Okay. Oh, thanks.
Thank you, Jorge. The floor is all yours. Ready for
co-presenter, Nilufar, was going to cover the second portion of this presentation.
Tu me laisses interrompre?
Very good. Good afternoon. My name is Alex Ajasi, and I'll be presenting a few drafts. The first one, it is EVPN, MVPLS, MVPN seamless interop. And next slide, please. Oh. So here are the co-authors of this draft, and the objective is as the existing central offices are getting transformed into the next-gen data centers, we're going to have a mix of MVPN and EVPN PEs in the same domain. And if the multicast VPN is a spread between these EVPN and MVPN PEs, question is how we're going to interrupt between them. One way to do it is have a gateway and go between the EVPN and MVPN PEs via the gateway, but that's not very efficient. And this draft talks about how we can do it more efficiently and considers three criteria. First one, basically not needing gateways in your data center if you want to go between these PEs. The second one, to give you a better optimum forwarding, among these PEs, so you don't have to do tromboning of the traffic. And if you want to go between EVPN PE to MVPN or vice versa, don't have to go to through the gateway. And the third is you don't have a gateway to provision it, so less provisioning. The requirements are pretty intuitive, have optimum forwarding among the PEs, whether they are MVPN or EVPN, optimum replication. So if EVPN, and so one thing I needed to clarify ahead of time is when we talk about EVPN, one can get puzzled and say, okay, EVPN is L2. Why the hell are we talking about the EVPN to MVPN, that is L3, interoperability between them? This is not L2 EVPN. This is IRB EVPN that does both L2 and L3. So the assumption in here is how you're going to interrupt between IRB EVPN that does both L2 and L3 and MVPN. And with the optimum forwarding, the assumption, optimum replication, basically what we want to do is have only a single tree for a EVPN IRB, for EVPN IRB, regardless whether the traffic comes from L2 or L3. So we don't have to do multiple replication. Support for all active and single active multi-homing needs to be done because that's the major feature in EVPN. Of course, inter-AS support needed, and we need to support all of the EVPN service interfaces that is captured in RFC 7432. Plus, we need to be able to do the very efficient L2 and L3 switching, so which means we need to be able to support distributed anycast gateway, support selective and aggregate selective tunnels, as well as optimize the storage of the host multicast state, which can be a star, G or S, G. To do that, the solution is very simple. Once you model it, okay, then you can see how simple the solution is. So we're going to model the EVPN PEs. If you look at the MVPN PEs, you can think of it as a PE with a bunch of IP verf. These IP verf are the US store host multicast addresses there, and these IP verf are connected to ACs. And you terminate host PIN protocol on these ACs. And then toward the core, you do BGP signaling, and you set up the overlay and underlay tree using RFC 65, 13, and 14. So we leverage that work, and we are saying that, well, if we model our EVPN as we have these IP verf connected, we know, well, this model is already defined. So this model is already defined in our baseline unicast PE. And we are leveraging the same model for the multicast, and we are saying that the IP verfs are connected to the MAC verf via the IRB interfaces. And by the way, these IRB interfaces can be considered as the ACs for the MVPN. So if you leverage that model, then you can say, my EVPN PEs can be modeled as a MVPN PEs connected to a bunch of MAC VRFs via these IRB interfaces. So basically, I'm gonna for the interoperability between EVPN and MVPN PEs, I'm going to treat my EVPN PEs at MVPN and talk MVPN language to the other MVPN PEs. So, well, that's all good and dandy, but there are few things that needs to be considered, and one of the challenging aspects is how to solve the all active multi-homing and a split horizon that we had on EVPN. How are we going to take care of it on the if you're trying to use MVPN protocol? And for that, how much time do I have?
You have burned 6 minutes, 7 nearly, and you have a 10-minute slot, and you have 9 slides to go.
So I'm going to be using...
You can decide to kill another presentation.
No, I think I'm going to cover the other, borrow time from my other presentation. So, because this is important. So I'm not going to get into too much of details, but we need to handle all active multi-homing in here. And the problem is when you do IRB, you cannot use the mechanism you've defined in RFC 7432 because that is only intended for the single bridge domain and not for multiple bridge domains and so forth. So what we do, we expand that mechanism, and we are saying that, okay, you know what, we cannot live, we are expanding the mechanism in EVPN VXLAN, which we call local bias. And we use that local bias in here, and we are saying that we're going to be doing that not just for a single bridge domain, but across multiple bridge domains. And the draft describes in detail how do we do that. So once you solve these main challenge, then the rest falls into its place. And basically, from the MVPN, then from IRB interface to the MVPN, to the IP verf, to the core, that's all MVPN procedures. So this slide talks about how we're going to do the blocking across multiple bridge domains in the same IP verf. As you know, it considers bunch of, a given IP verf is connected to a bunch of MAC verfs, and each MAC verf is represented by a single bridge domain, and how the local bias mechanism can be extended to handle loop prevention in case of the all-active multi-homing. So that covers the first part of the presentation. The second part of the presentation, Nilo is going to talk about the solution, how we're going to cover it for the intra-DC, and the procedures that we can use to take care of the intra-DC scenarios. Sure.
Yeah, so as Ali mentioned, this solution applies also to the DC, and we have actually implemented it with Ashutosh and others, and there are customers waiting for its delivery. So Ali went through the modeling very well. I don't repeat it here. So the EVPN IRBPs are modeled as MVPN, and when traffic comes from a local source, it's routed to local receivers behind different MAC-VRFs, or it's bridged to local receivers on the same MAC-VRF. If there are remote receivers across the fabric, then traffic is delivered to the fabric via the IP-VRF, and it's encapsulated with the IPMZ or SPMZ encapsulation associated with that VRF. On the egress leaf, traffic is received on the IP-VRF, and if there are local receivers behind some MAC-VRF, it is delivered to those receivers. One important aspect of our solution is that the tenant multicast signaling terminates at the IP-VRF, so we save bandwidth. Inside the fabric, the tenant multicast signaling is delivered via BGP MVPN. Other important aspect is that there is no dependency between the instantiation of MAC-VRFs on different PEs, on the ingress and the egress. We also support selective MDT. BGP advertises a mapping between the tenant source and group and the underlay source and group using SPMZ route, and only PEs which are interested in a particular tenant source and group will join the underlay tunnel. Some diagrams to clarify. We have different settings of the receivers. So there is a source behind MAC-VRF1 on PE1. If there's a local receiver behind MAC-VRF1, it's just conventionally bridged. But for receiver 1 on PE1, traffic needs to go to the IP-VRF and route it via the IRB interface. Also, all the PEs that are part of this MVPN, they join the IPMZ tunnel. In this case, that white tunnel. So if there is some remote receivers like on PE3, it will send out joins to PE1 in the BGP MVPN address family, and the PE1 will deliver traffic through that white IPMZ tunnel. So everyone, including PE2, will receive that traffic. But on PE2, since there's no local receiver, traffic is dropped. On PE3, it is routed to receivers behind MAC-VRF 2 and 3. This is the SPMZ case. So in this case, PE2 doesn't join the tunnel because it doesn't have any local receiver. So we are saving some bandwidth here. So the VXLAN DC can interoperate with the MPLS WAN. And when we say MPLS WAN, it can refer to legacy MVPN over IP MPLS, RFC 6514, or it can be the MVPN EVPN IRP proposal that we are presenting. But we will need gateways in this case because the encapsulation on the two domains is different. And usually for redundancy and load balancing purposes, we have more than one gateway between two domains. So we have to address the multi-homing between the gateways. So in this case, we have a source behind MV1. That source is viewed by any receiver on MPLS domain as a multi-home between the two gateways. And note that any signaling that comes from one domain to the gateways is reoriginated on the gateways with the gateway next hop. So that's why On the other domain, the PEs don't know anything about the details on the other domain. So in this case, receivers in the MPLS WAN sends the join to both the gateway and the traffic from source lands on both gateways and is delivered to the MPLS WAN. If there is some inclusive tunnel on the MPLS WAN, this traffic may get received by Gateway 2. But Gateway 2 has an RPF looking to the source on VXLAN-DC. That is why the traffic drops on Gateway 2 and there's no loop. But if there are some local receivers on Gateway 2, the traffic should be delivered on Gateway 2 per regular multi-homing procedure. I guess I have to skip this slide. This is a case where the source is behind Gateway 1. You can go over the draft and learn more about it. Sorry. Any questions?
Jorge Rabadan, Nokia. Not sure if it is a question for you, for Ali. Well, we discussed already a few issues that, and there are a lot of holes in the document or things that are not explained yet, I guess. But one of the things that
there are not a lot of holes. We discussed two, and I mentioned what are those and how to address them. But I think to make sure that we are not missing anything, let's definitely discuss it and list them.
That's fine. Can we go to the that diagram where you have the multi-home C? I don't know where was it. That one, for instance. Just a question about this.
Okay.
So let's say you have behind the switch, you have a source, and you have a receiver behind P3. Okay, and you have all active multi-homing. So because you have all active multi-homing, the multicast traffic can be hashed to, let's say, P1. My question is, if your receiver is in behind P3, how do you make sure that P3 in the UMH selection picks the right P1 and not P2?
Because we're doing it via the source active discovery, and PE1 sends a SA discovery, and PE3 knows where the source source PE is and hooks up to that.
How do you discover the source?
Via the live traffic, the same way as MVPN.
So when you receive traffic?
Yes.
Okay, that was my question.
Okay.
Thanks.
So I don't know if you already mentioned in the draft there are some caveats with this solution.
Right, there are going to be some scenario that we discuss offline. Yeah. I'm going to mention that explicitly. Okay. That those those scenarios probably not covered. If we cannot come up with a solution for those scenarios, it's going to be explicitly mentioned.
Yeah. Okay. Thanks.
Sure. Any other questions? No? All right. Thank you.
So, Ali.
Next one, right?
Well, you have, I guess, pretty much 10 minutes to do your two presentations. Even less.
Okay, so I got till 42.
Select one, IP aliasing or DPLS or active.
Let's go to IP aliasing and so we got I got till 42, right? For all the presentation.
Are you doing a Niraj or?
No, including Niraj. We're gonna do it, including Niraj, because Niraj is gonna be taking 5 minutes, maybe 6.
You have until 40.
Okay.
but you won't be able to do LSP ping.
No, LSP ping is going to be 5 minutes at the end. Because
No, but I have a 10-minute presentation. Ali, you took 20 minutes for that one.
Okay, that's fine. No, that's fine. Okay, so IP aliasing. This is going to be very simple. Basically, the IP aliasing in EVPN has been defined for the L2 routes for the MAC addresses. And then when you do IRB, there are two flavors of IRB. One is symmetric, one is asymmetric. Asymmetric gets resolved to your local MAC addresses, so you can leverage the IP aliasing already defined for the L2. When you go to the symmetric, then the symmetric IRB needs the IP aliasing at the IP routes, and this draft covers that, and it is pretty straightforward in a sense that I could have covered that in the existing IRB draft, but it has gone through the working group last call, and that's why I put a new draft. So I'm not going to cover what the aliasing is. The first slide talks about what the aliasing is. We don't have a time. We assume that everybody knows the aliasing procedures for EVPN. And in a nutshell, this proposal leverages the exact same procedure of EVPN aliasing, which we do for MAC addresses. It says now use it for the IP addresses for the symmetric IRB. And once you do that, the fast convergence using the mass withdrawal and all that works. So it is a short draft. I encourage you guys read that. And as I mentioned, this is to cover the symmetric IRB case. Go ahead, all right.
Jorge Rogadan, are you planning to include the RT5, or you don't think it belongs here?
RT5...
I mean, for mass withdrawal, not really for aliasing, because that's given.
Exactly. But
it would be nice to have it all together.
For that? Okay, all right.
That's one thing. The other thing is, for aliasing for RT2s, if you learn the MAC and IP binding through gratuitous ARP, and basically you hash it on one link, right, and you bridge to the other guy,
right,
and you discover them both, you're going to advertise it from both Ps. So in that case, you don't really need any aliasing, right?
Then with the same token, we wouldn't need the aliasing for the baseline EVPN.
Yeah, but in baseline EVPN, you can receive, unicast.
But the same principle applies in here. In other words, if you receive it on both, you wouldn't need aliasing because both will send. However, you cannot assume you're going to receive it in both, because it can get traffic and get hash. Both ARP traffic as well as the ARP message as well as the traffic can get hashed into the one link.
Yeah, it depends on how you learn the IP, really.
Yes.
Okay.
So hopefully very quick question.
Yes, very quick. So in this draft,
yes,
you assume that the BD route target and the L3 route target are different, right?
What was the first one?
The L2 route target.
Yes, and the
L3.
Well, one is MAC, but the other one is IP.
Yeah, but you are using the EBI AD route in both, right?
I'm gonna be using two different RTs, and the EVI. No, the EVIs are different. We use two different EVI or VNI. One VNI corresponds to the L2, the other VNI corresponds to L3. Yeah, one VNI corresponds to MAC-VERF, the other VNI corresponds to IP-VERF.
So should we maybe put a note that they cannot be same otherwise?
Absolutely, absolutely. Thanks. Okay. Next one.
Which one do you want?
VPLS.
All active?
Yes. And then after that, I think it is Neeraj's.
If you're making 2 presentations, it's 5 minutes
Each. Right. Well, for you, I do mine in 4 minutes, and I give 6 minutes to Neeraj.
4 minutes, 9 slides.
Yeah.
Okay.
I did that same thing.
Go.
All right. So we had a draft a couple of years ago on EVPN, VPLS, how they do a seamless interoperability, and we ran into issue for all active. So that draft was limited to single active, which means active standby multi-homing. And that has been implemented by multiple vendors and is a working group document, which we're going to request for a last call. And this draft covers the scenario that instead of single active, you have all active. And all active, the reason we didn't address it at that time because it wasn't as straightforward. With the all active, the issue is when your CE device, which has MAC-D, wants to send the traffic to your MAC-A, when you have all active, the traffic gets hashed for the same VLAN to both PE1 and PE2. And these EVPN PEs, if they have pseudo wires to VPLS PE3, so for the same source MAC and the same VLAN, PE3 receives it via 2 pseudo wires, and in terms of its learning, is going to flip-flop between the 2 pseudo wires, and it's going to trash PE3. So the question is, how do you solve this MAC flip-flopping when you have all active EVPN? And all active EVPN is very important. It's one of the, as I said, key feature of the EVPN. So to address that, we do it very, simply. We are saying that we're going to be using the concept of the Miro pseudo wires, and for a given PE, for a given EVPN PE, based on the DF election on that Ethernet segment, on that Ethernet segment, based on that DF election, if it is a DF, then that pseudo wires becomes DF, and we're gonna PE2 will use the same pseudo wire label. Okay, so that's why we call it mirroring, because PE2 uses the same pseudo wire label as PE1. When you do that, PE3, when it receives the traffic, it basically assumes it receives the traffic from the same originating PE, and it avoids flip-flopping. So the advantage of that takes care of the MAC flip-flopping, and the traffic from the EVPN toward the PE, it gets load balance across both pseudo wires, but from the VPLS PE to EVPN PE, it gets sent via only a single pseudo wire. But that's okay. I mean, that's the way the VPLS works anyway. And the load balancing is basically asymmetric in one direction. From EVPN PE to VPLS PE, the load balancing is done on a per flow basis over the core. In the reverse direction is done on a per VLAN basis over the core. So that basically it. And the draft talks about what the control plane changes needed. We can leverage a lot of EVPN and ROS, and basically very minor changes is needed on the control plane, and a bit of changes needed in the data plane. But it discusses in detail what those changes are. And it talks about also how you handle the multicast traffic versus unicast. Or I should say bomb traffic that covers multicast, broadcast, and unknown unicast. So it's an interesting draft. Definitely encourage reading it. It is the second part of the draft that was written a few years ago that we didn't have a solution at that time, and this now proposes a solution.
You took 6 minutes.
6 minutes. You got
4.
4.
Good afternoon, folks. Neeraj from Cisco. These are the co-authors. I'm going to be talking about extended EVPN mobility procedures for EVPN IRB use cases. As the title suggests, the main objective of the draft is to define mobility procedures for MAC and IP for all EVPN IRB use cases, and the work here is based on top of MAC mobility procedures defined in 7432. So essentially, we classify all the mobility use cases for EVPN IRB into three main categories. Scenario A, where the MAC IP bindings are always fixed across a VM move. Scenario B, where a host IP could move to a different IP binding. And scenario C, where a host MAC could move to a different IP binding. So for the scenario A, it's pretty much the existing MAC mobility procedures can be leveraged and applied to scenario A. It's the scenario B and C with changing MAC IP bindings that are complicated by the fact that in EVPN IRB, we advertise both MAC and IP reachability via a single MAC IP route type 2 with a single sequence number attribute attached to that route that signals the route version for both MAC and IP components of that route. So essentially, if I have an IP that moves to a different MAC binding, now how do I assign sequence number to the new MAC IP route? If I treat it like a fresh route and assign a new sequence number, then the mobility for the IP component would not take effect because it's already advertised with a higher sequence number. Similarly, if the MAC moves to a different IP binding, if I treat it like a fresh route, assign it a new sequence number, the mobility for the MAC component of the route would not take effect because the MAC is already advertised with a higher sequence number. So
you don't have much time left.
Okay.
Blame
So,
Ali, but
okay, just
2 minutes.
2 minutes. Okay. Sure. So basically, the solution that is defined, the key part of the solution is that we associate the sequence number attribute only with the local MAC component of the route. So only with the local MAC route, and the MAC IP essentially inherits the sequence number from the parent MAC. And we define two key rules that must be followed when assigning sequence number to the MAC. The rule 1 is essentially same as the existing MAC mobility rule. And the rule 2 is essentially that when I learn a local MAC IP route, the sequence number assigned to the MAC component must also be higher than any older MAC association for that IP. So essentially, with these rules in place, I'll skip the baseline scenario, but essentially when the IP moves to a new MAC binding, rule 2 comes into play, and the new MAC binding gets assigned a sequence number that is higher than the older MAC binding of the IP, and the MAC IP essentially just inherits the parent MAC sequence number. When the host MAC moves to a different IP binding, then essentially the existing rule 1 again applies, and the MAC IP simply inherits the parent MAC's sequence number. So just a few other things that are also covered in the draft. It covers the MAC sharing scenario where multiple IPs could share the same MAC binding. It also defines a duplicate IP detection procedure for the use cases where the IPs might be misconfigured with two different MACs, something that wouldn't be covered with existing MAC duplicate MAC detection procedure. And it also talks about sequence number synchronization across redundant PEs. So that's basically what I had.
Sorry, Jorge. I would have loved the discussion, but we're not taking questions. Just to respect Kilraj, who is across the world. Thank you.
So maybe we can discuss over the list or...
Okay, Raj, do you hear me?
Hi, yeah, this is Kaliraj.
Hi. Okay. You can start. I am the one going through the slides, so indicate me whenever you want to change the slide.
Yeah, so hi, this is Kaliraj.
You have 9 minutes.
From Juniper Networks. Today I want to introduce you to this draft, which basically talks about how to create private MPLS namespaces, which is private labels using BGP. Next slide, please. So basically, this is a problem statement. How do we achieve predictable label assignment at a receiving router at a router who is not me myself. So as we know that MPLS has locally significant label allocation semantics. So with that in mind, how do we get a predictable label allocation at a router? So it basically combines two RFCs together. We know the upstream label allocation, that is RFC 5331, and we have our 2547 VPNs. So if we think about it, 2547 VPNs provides us a different forwarding context for IP. So this mechanism basically reuses 2547 and uses extends the signaling to provide private MPLS context for MPLS forwarding. Next slide, please. So here I'm trying to explain what context tables are and how do we use it for an off-box label allocator. So in this diagram, I've shown a router which has its own locally allocated, locally significant labels in its blue fib, which is the MPLS fib. And we see that this router is connected through two interfaces. As an example, the G000 is a shared common interface which kind of goes to the core. And G200 is kind of a private interface, which comes into a specific forwarding context. You can assume this is like a interface that comes into the CE/VRF for L3VPN. So if you think about it, this is very similar to L3VPN, where A.MPLS.0 is instead of A.ANA.0. And the MPLS.0 global fib is the core. So the CL1 is the context label that is locally significant, and it points to the A.MPLS table. So taking the parallels with L3VPN, the CL1 is like the VPN label. And whatever traffic comes inside that is a PL1. That becomes a private label. So I can have multiple routers in the network where I create the A.MPLS fib, and I can install the same label value PL1 so that I am able to deterministically get the same label value at different routers, using which I create this private MPLS fib on a shared MPLS network. So this way, users can create multiple MPLS planes in the network and use them with their own label values with desired forwarding semantics. So that is the main idea. And each MPLS plane is actually identified by a context protocol next hop. Just like LO0 identifies one router in the network, so the context protocol next hop identifies one MPLS plane in the network. Next slide, please. So this slide basically explains the constructs, and some of the constructs we described in the previous diagram. So the main thing I want to point at this slide is that each MPLS plane that is identified by the context protocol next hop, the service routes can bind to this MPLS plane by using that context protocol next hop address as the protocol next hop in the BGP update. And the label can be a private label that the application itself allocated. Next slide, please. So these are the protocol extensions that are being done for this mechanism. The first draft is what we are talking about right now. That is the 4364 style extension to provide BGP signaling for the private labels. So second draft is the multi-next hop attribute, which basically allows a BGP route to carry multiple next hops with different forwarding semantics, which could be a forward, push, pop, or swap. The forward is applicable for both IP and MPLS traffic, but push, pop, swap is applicable for MPLS traffic. Next slide, please. So these are the details of the route types that this mechanism provides. So the first route type is called the context protocol next hop advertisement. Every router that creates a context fib A.MPLS for a MPLS plane A advertises the context to other BGP speakers and applications. So prefix is the RD : context protocol next hop address. So as we already mentioned, context protocol next hop address is the same IP address on each of the routers which are participating in that MPLS plane. So the RD is the one that uniquely identifies each instance router. So, and the attribute of this route would be a multi-next hop attribute, which would just say push the context label towards me, where me is the global LO0. And all of these routes have the route target identified in the MPLS plane because it is just a L3 VPN. Next slide, please. So once the context has been advertised to the applications, now the applications can install their own private label values into the a.mpls context, just like we do install the L3VPN IP VRF routes. And so the prefix is nothing but a RD colon label, and the forwarding semantic can be anything that the application wants, which could be identifying a certain resource, which is a next hop that is attached to next hop interface that is attached to the MPLS plane, or a VRF that is attached to the MPLS plane, or when the route is getting re-advertised to other speakers in the MPLS plane, it will be forwarded to me, where me is identified by RD colon the context protocol next hop address. Now, the RD colon context protocol next hop address is resolved over the type 1 route that we saw in the previous slide, which is how we push the context label over the private label to reach to hit the correct context fib. Next slide, please.
Kaliraj, you might want to think about leaving room for questions.
Okay.
You have 2 minutes left.
Okay. So this slide has a lot of detail, but if you think about it, it is very similar to L3 VPNs. So PE1 and PE2 are like the CEs in L3 VPN, which come into a forwarding context. And once we come into the forwarding context, we are in an MPLS plane, and we use the same L3 VPN context label to remain in the same L3 VPN plane. I think I'm 7 minutes now. So next slide, I have shown an example of a use case. I think next slide. So here we have a case where we have a virtualized environment, and a bunch of routers are VCVPE1, which is a conglomeration of VCP and VFP1, VFP2. And there is a fabric interconnecting all this. So there is an upstream node, the service forwarding helper, which basically is getting all the traffic that's coming from the core. Now, the problem that here we want to solve is the service forwarding helper needs to direct the traffic towards the right VFP so that we don't have an extra fabric hop in the virtualized environment. So the way we are solving it using this mechanism is VP1 is able to have a context fib for itself at the SFH, and he is able to program the routes that he allocated locally significantly in his MPLS.0 into the VP1.MPLS. So that when the traffic comes from the core, SFH knows exactly whether the label L1 is behind VFP1 or VFP2. So this is one use case. And because this just makes an API into the network's forwarding plane, I think more use cases can emerge. So the backup slides have more use cases described that you can have a look offline. That is what I had. I think I can take questions now, if any.
Anyone for questions? If not, I'm closing the session. Thank you, everyone. Thank you, Kaliraj, and see you in Singapore.
Thank you.
Goodbye, everyone. Where are the blue sheets? If you see them next to you.